So it's a tag team. I'll start, Rick will cover some geology. We had to get Yins into the title because I am a native Yinzer. And so this is our unofficial title. It does cover the topic that ASCE renamed it. So this is the summary of what we're going to talk about, and rather than read all those words, Rick suggested I tell you a little bit about a picture on the left which has nothing to do with Pittsburgh. That's the World Trade Center liner wall, and it helped me recover from witnessing September 11th. But the truth, so what's exposed on the very left is the original slurry wall, diaphragm wall from the World Trade Center bathtub. And those are kind of the anchors we put in to do the recovery work. And that's there so you can see it. I will tell you that those anchors don't really support the wall anymore. And that's all I can tell you. And I don't have any drawings either. So we're going to start with a safety minute. I went out to stress these 4-strand anchors. And we were stressing them using a hammer. We call it a hammer because the guy who started us using it's from Boston. And it's this little device right there. So what you do is you raise and lower that, push it, hammering it on the wedges to hammer them in, and they kind of go thwack, thwack, tink, tink. So when they start making a higher sound, you know they're in. And this particular one wasn't sounding right to me, and I didn't like how high the wedges were sticking up, so I was throwing harder and harder, and hard enough that my thumb hit the chair and the nail got torn off, rotated off, and that blood is all laceration. And this was a picture that I sent to the nurse I was talking to on the phone when she said, go to the hospital. And this was the outcome of the hospital. I don't remember how many stitches. And it became OSHA reportable because there was also a broken bone in there, and they gave me antibiotics to deal with that because it was an open wound with a broken bone. And that made my personal TRIR really poor, lifetime really poor. Okay, turn it over to Rick. Talk about geology.
What's the button, Tom?
The green one.
This is the green one?
Yeah, sorry.
Okay, all right. Good morning, everybody. Welcome to all you visitors. We're really happy to have you here. My job here is to talk about the geology. Tom did all the heavy lifting with all the other work. And, you know, geology's got a lot to do with the presentation we're going to give, but also you'll see a number of case histories where it'll be relevant. And there's a publication that we have locally that made my job pretty easy by Dick Gray et al. And it's a really outstanding document, and to be completely honest, the content that I have, pretty much 90% comes from this document. Dick Gray is really an icon in this area, and many people have been mentored by him over the years. He's been in this profession for over 60 years, active in industries throughout that time, and really a remarkable person. So I'll start off with a map of, or a geologic map of Pennsylvania, and the sediments that are below us now are really of Pennsylvanian age. You'll see there that it says that we're in an Appalachian plateau. I don't know about you guys, but this doesn't feel what I would define as a plateau. So there's a two-part story here. A little bit to the southwest, we got a little bit more recent deposits in the Permian. And then to the east of us, we've got older deposits. And all these sediments come from erosion from a tremendous mountain range that was formed on the east coast of the United States. And during about 300 million years ago, the North American plate and the African plate ran into each other and collided, and over a period of sequences, and created a tremendous mountain range on the east coast of the United States that was paralleled the Himalayas and Rockies, and it was a major mountain system. And you also notice here that this is the location of the land at that time is on the equator. So essentially, all these deposits were really depositional deposits in shallow seas that were being eroded from the major mountains into the east, and those mountains deposited, or the erosion from those mountains deposited hundreds of feet of deposit, and these are the Pennsylvania Age deposits. The specifics depended upon how deep the oceans were at the time, so we've got deep water limestones, we've got shallower water sandstones, and then the siltstones and claystones in between. And we also have something that's characteristic of this area, which is a lot of coal, and that coal comes from huge, expansive tropical forests that were here at different times and were subsequently buried, and that's where the coal seams come. And the main coal seam in this area is the Pittsburgh seam, and it's the largest resource of coal in the world, and it's still being mined in the southwest part of the state, in West Virginia and Ohio. I appreciate that this figure is not very clear, but I just wanted to use it to remind myself that we've got also what we call red beds in this area, and these red beds are non-durable claystone deposits that, when weathered, become very weak and have contributed to lots of landslides in the area. Here, right in Pittsburgh, we're below there's been erosion enough to be below the Pittsburgh coal, but as you work your way to the southwest, it's still prevalent. And I know for myself, because my house was mined with it and had subsidence years ago. So the next part of this story, so that explains how we got to the plateau portion of this area. And then the next part of the story really comes from how did we get from a plateau to this very hilly and land with valleys and ridges. And it really comes to the impact of the glaciers. The glaciers did not come and cover this area, but the meltwaters from the glaciers had a big influence on the topography and the deposits that we have. Prior to the glacial advances, the rivers in this area all flowed north. And so we had the Allegheny was actually three different legs of the Allegheny. Then we had the Monongahela, or the grandparents of the Monongahela, and the Kanawha rivers, the Ohio, and everything's flowing north. And then what happened is the glaciers came in and came up above north of Pittsburgh and essentially dammed all those rivers. And so those dams caused flooding of all the river valleys, deposition of clay deposits, and I've had own personal experience where we have really lacustrine clay deposits, and glacial lake clay deposits, and at Marmet Lock and Dam, where there was several feet of this clay that was very sensitive material and very unusual for this area. Those dammed rivers overflowed, and the drainage paths changed, and instead of everything going north, now it all went into the Ohio River and went west to what's now the Mississippi River. And during that process, we started at the top of this figure on the left-hand side, and it really shows the Pittsburgh area with the ancestral Allegheny and Monongahela rivers on top of a plateau. And then as the glaciers came in, the amount of meltwater that was present created huge flows of water that caused substantial erosion in the area. And so as you work your way down, you're seeing the influence of glaciers over time, the deposition of glacial deposits with Canadian shield igneous rock as you work your way down. And so you're seeing the Pittsburgh downtown valley there down at the bottom, which was substantially impacted by glacial deposits. The figure on the right shows the Pittsburgh area, and well, I won't try to use that, but you can see the grayer area there is all elevated terrace deposits. So those were all parts of rivers with substantial coarse grain material deposited at higher levels, and then there's the rivers cut deeper. They were left stranded up there. And Tom's going to talk about that in detail, because not only do we have the Pennsylvania rock here, but we have all these terrace deposits throughout the city that hold water sometimes, and so they can pose challenges to the geotechnical engineers, especially as part of supportive excavation systems. And the last figure I have is just an example of what some of these glacial deposits look like at depth in the river. And you can see the gradations there. It may not be obvious from out in the audience, but these deposits, there's about 60% gravel size and about 40% bigger than 2-inch material. And so these kinds of coarse deposits are down deep. They're not soft rocks or igneous rocks. and you're obviously not going to be sampling them with a split spoon. So with that, I'm going to turn it back over to Tom. Thank you.
So now we'll talk about the different wall types that we've used around Pittsburgh and how the geology mostly influenced them. You'll see that I have found several weren't necessarily geology. And back in the 60s, 70s, it was sheet piles and rakers. And I don't know much about those jobs because I was just a wee little kid then. But we'll start covering projects starting at about 1980s, and the dots are all the different projects we're going to talk about, the pins. We'll start in downtown Pittsburgh, kind of work our way along some rivers, and then get up into the Shadyside, Oakland area in here. And what's interesting is if you just kind of eyeball that old map onto here, and you can kind of use the green, hilly terrain areas to draw the lines, and it's remarkable how our development of the city almost replicates the spots where the river used to be. But we'll start at PPG, a rather iconic building here in Pittsburgh. You can see it if you go look over the river. It was in the Batman movies, and not the one that the most famous Yinzer, or more famous than me, Yinzer, Michael Keaton was in. And it was actually written up in a paper by Peter Nicholson and Philip Wycliffe Jones in 1984. I know about this job from talking in the bar with one of my superintendent mentors. Pete Nicholson never mentioned it to me, which I find a little strange. I started working there in 1988, and I wonder if it's because it was what we call technical success. But what we're going to talk about is some soil nails that were used there on portions of the project. So on the left is the profile. The red line is the bottom of excavation. Shoot. Can I go back one? The red line is the bottom of excavation, and you can see where the excavation is going to go about 7 feet below the groundwater table, and that groundwater table is pretty real. That elevation 710 agrees pretty well with the elevation of the rivers here in town. So the red walls were done as soil nails, and I'll explain that the reason it was done was because of geometry, and we'll see how that applies in the cross sections. The other point I'd like to make was that dewatering was possible here because an impermeable layer in the shale was at greater depth. So you could put in a well and draw down curves that made sense. If that rock was way up shallow, right near the bottom of excavation, now you can't get drawdown laterally or into the page, let's say, between your wells, and that's called slurping. And that's an official dewatering term that I learned from Paul Schmall, who's my dewatering guru. So we think the watering was done with well points. Pete's paper doesn't really cover that. So it started out as a kind of typical thing where there's a basement wall and a footing, so you support that as you start digging next to it. But then you put in a micropile, that's pretty typical. But then there's these weird 5-inch grout columns that are battered 1 on 12, and that's where things start to get interesting. Because what they were doing was putting in this battered mini soldier pile wall. They were drilling 5-inch holes and pressure grouting them, looking to get 1-foot diameter grout bodies, drilling them almost on 1-foot centers. And the idea was to make a facing out of that, put a rebar in there, and that becomes the facing. What we do nowadays is put in piles like that for face stability, and we just kind of started doing it. Actually, we're working with John Byrne, who wrote the FHWA manuals. Pete never really shared it, but it's really interesting that that's what they did for the facing. And then because it didn't have continuity into the page, they had an external wale. And the reason for this 1 on 12 batter is to make the geometry fit where this footing here has a heel on it, even though the built might be thicker walls down here too. So it was all driven by zero space shoring. And that reminds me of another job that we did that was slightly similar. And that's the old Civic Arena. This is just towards downtown from the Civic, where the Civic Arena is. The hockey game will be played over here. And in this case, we had to go with a thinner wall using micropiles because there was a gas line existing on the sidewalk, and the Mellon wanted to build their structure up to the property line. So again, geometry made us do it. Okay, now we'll move on to a different type of wall on the north side. This is Ramp Q. Seth Perlman wrote a paper about it. We'll see some of the stuff from that paper. And throughout the East Street Valley, there was a big development there in the 1980s. And throughout that valley, the walls were done with drilled shafts, reinforcing cages, and shotcrete. And this particular one deserved a paper because it was one of the first tieback supported bridge abutments. And there's a cross-section from the paper, and we'll see in the next slide that that's really mostly colluvium. So even though this looks like it's right at the edge of where that terrace is mapped, it really wasn't terrace deposits that affected this project. And certainly further up the valley with all the other drilled shafts and shotcrete walls, it was just residual and rock. But there was colluvium on this job, and they knew it because when they were making another excavation, there was movements. So there's the words that prove it's colluvium. And from the other abutments, they back calculated a residual strength of 12 degrees and phi equals 0. And they used that in both the global stability checks, but also in the apparent earth pressure diagrams. And we'll see an impact of that. This is the most technical part of this talk, by the way. Everything else is just stories. So these figures were in the paper. It's about the performance of the wall. And when I showed them to Rick, he said, wow, why do those anchors lose so much load? And I was like, I don't know. And I kept digging and reading and realized that this wall movement is actually backwards. They're pushing the wall into the soil every step of the process. And maybe this will lead into the next discussion, but my theory is it's the 12-degree friction angle doesn't apply to the whole soil mass. It applies to the soil mass on discrete planes that got forced to be at that residual shear strength. And so when you design using apparent pressure diagrams that already have 30% more force in them, and use a Ka that's from residual strength of a failure plane that isn't even within the mass you're trying to support, you're gonna overload the wall and push it back. But it still performed, it just went backwards. Seth wrote a paper about another wall that did something similar, also on a landslide. Okay, so now we're gonna move on to soldier pound precast walls. They're mostly along a river, and even though they fall in the yellow dot areas, so there's some stuff on Route 28, Nan Street, and Sycamore Street, which is so close you can walk and see it, and I drove by it coming in this morning. So we'll move on to these walls. And the reason for these walls is because of those soft rocks in our profile, especially below the Pittsburgh Coal, Route 28, the Pittsburgh Coal is 300 foot above where we're standing now, right here. We're up on the bluff. And so this stuff's all older than the Pittsburgh Coal. And this includes some of the red beds in the picture and the profile Rick showed before. And there's still other clay stones in there too. So you got some resistant rock and then this wheat rock, and you can see that the talus down here is encroaching on the roadway even with the slope being that flat. So the reason that the DOT wanted so many retaining walls built was so that they didn't have to make these big flat cuts and have drop zones for rock. It all became a space issue. Boy, can you call this one attributed to geology, or is it geometry? But it's really geology that led to the need for these sloped cuts. And so this is a retaining wall built right in that same area, probably within a few hundred feet, maybe 1,000. This was actually built by others, but it's a classic wall that was built for PennDOT with soldier piles, usually pairs of soldier piles with the anchors going through them, and precast lagging. So now we'll come to Sycamore Street. It was before that last picture. It was one of the earlier ones. And you can walk there from here. On the left is a picture from the original construction, and on the right is what you can see from Google Earth nowadays. So here it is performing. Seth will know exactly what year, but I'm thinking it's 1987, 1988 that wall was built. 83, wow. And I can tell you from my inspection driving down there this morning that the anchors look pretty good, except you can see this black little streak coming out from the anchor caps. And so I would encourage you that if you don't have restressable, and it's not the first time I've seen this phenomenon, I know what to look for. If you don't have restressable anchors, fill those anchor caps with grout and avoid that black streak and the maintenance. So then we move on to Ann Street, and Seth's probably going to be mad at me for putting those words up there, but the newspaper article called it the monstrosity. And it's a precast wall. The anchors bounce around, so they're not in a nice even line. But really, I think what made it not look as aesthetically pleasing as the other walls were those were 4-foot panels. And the 4-foot panels don't have the same aesthetic as the previous picture with the 1-foot panels. And certainly, even if you do 2-foot panels, it looks a lot better. The other thing is these panels joints don't match up. So if you can make them, even you can fake a joint in there and make them match up, and things look a lot better, and maybe you don't get a newspaper article calling it a monstrosity. Okay, now we're going to move on to the walls affected by terrace sands. And these are, so those ones, even though they're mapped in the terrace area, the elevation's all too low. All those terrace things where the rivers used to be got eroded eventually. And so the terraces are at higher elevations. Like the locals will know, Oakland is up on a bluff across the river. So it's, 400 feet higher than down here at the river. Route 28 was pretty close to the river. Sycamore Street, they're all down near the river, so the terraces don't affect them, they're gone. So the first job out there is a pretty old job, and I don't have any idea what year it is. This picture I actually got from Jerry DiMaggio when I used to teach classes with him, and that's a tangent pile wall. And it's the only tangent pile wall I know of. And it's still in place. If you go in the parking garage at Montefiore Hospital, you can see this tangent pile wall. Tangent means that the circles almost touch, or in theory, perfectly touch. If you go in there, you'll see those same looking shafts, rough looking, and maybe a little bit of shotcrete and dental work down in the cusp of where they meet. 1980, you said? And what really caught my eye when Jerry first showed me this picture was that mast, because that was the original Nichols and Anchorage Company mast. So that kind of helps date things. Now, even though this was in that terrace map, it is probably 40 to 50 feet higher than Fifth Avenue, right there in the heart of Oakland and the University of Pittsburgh stuff. And I'm not sure that there were terrace sands on this job, because we've worked at the other hospital, UPMC hospital, Presby stuff, and I don't remember there being terrace sands on those jobs. So I don't know exactly why they chose tangent piles. We're not even sure who did them. But it's interesting that they were used. It's kind of the start of trying to do something to deal with these sands. So now we'll move over to Soldiers and Sailors, which is right here, not too far away, but like I said, 40 foot lower in elevation. And this is down where Oakland is kind of flatter. And nearby, about a block away, there was a Holiday Inn that was being built, and it used soldier pile and wood lagging shoring. And in this particular case, rock is at the bottom of excavation, like it was at the Holiday Inn. And so now, when you get down and you're in the sands, these terrace sands, and you get down near the top of rock and the water's coming at you, you're going to lose ground. And you can try to de-water it, but because you can't put in a well that will actually connect to it, you got to have a whole bunch of little well points, and you're trying to slurp the water like your milkshake at McDonald's off the top of that rock. And so that led to some loss of ground. I remember it, the damage on the street. It was, and so when they wanted to do something here in front of the soldiers and sailors, which is a nice historic structure, they didn't want to have any loss of ground. And so we came in and said we can do diaphragm walls. Back then we just called them slurry walls, but diaphragm walls are the preferred words nowadays. And so this was the first diaphragm wall done in the city of Pittsburgh. It was the second one done in western Pennsylvania. So there it is on the map, the star. So we had indications it was going to have the terrace deposit issue. I don't remember how much water there was above the rock here, maybe just 5 foot of water, but we went to the diaphragm wall choice. That particular diaphragm wall, we used pipe end stops, which are no longer done anymore. And I designed it all in a spreadsheet. Probably did the reinforcing calcs in MathCAD. And then we put in the anchors. And there was a final excavation with the historic structure in the background. This all became part of a parking garage. It stopped on rock initially, and down at this end here, there were the excavation actually went into rock. And eventually the superintendent from the GC said, man, if you guys just dig a couple more feet, you're going to get down to the right grade. So we got paid extra to chisel out the rock and take the wall down. There are a few panels there that stop at the top of rock, and there's exposed rock in there. And there's the completed project. Now we're going to move a little further out, but more into the heart of this terrace deposit. And this is in Shadyside at Shadyside Hospital, and there's 3 projects right close together here that we're going to talk about. And these two are only about 600 foot apart. And so I'll start with this cancer center and then wrap up with Morrow Park because of chronology. But I want you to remember to look for something different in the geology at those two. So the cancer center, we ended up choosing micropiles as soldier piles because there was this pretty substantial cap rock. I think it was sandstone. Could have been, yeah, it says sandstone right there, sandstone. And as you can see, there was no groundwater problems at the bottom of excavation. There was, however, sand here. And we'll see some impacts of the sand even though we were high and dry from a groundwater standpoint. And so the micropiles were chosen as soldier piles because of the cost of socketing into the rock. We looked at both, and micropiles ended up being cheaper. Down in the rock, we used rock bolt soil nails in the claystone. And I'll tell you, as a sanity check, I made sure we had a factor of safety of 1 with phi equals 15 degrees for that claystone. But only 1 because I didn't think it was highly probable that the orientation of the 15-degree planes would be the perfect active failure wedge for a soil nail wall. So here's the impact, and I just can't get good pictures. You know, it was before the age of digital cameras. You can see some clay material at the top, and we're starting to get into the sand. And we had some rat holes at the top that really were about how the general contractor chose to excavate, maybe putting a rookie guy on the excavator. But when we got down to the next level and other places on the site, they were hoe ramming that hard cap rock. Those terrace sands, even though they were just moist and had some apparent cohesion, they lost it with the hoe ramming vibrating things and caused a loss of ground and caused these rat holes to continue. We really fought them throughout the project because of the terrace deposits. So then we go to another job like within the next year. This is just a few blocks away. I can't really remember if their terrace deposits were here from the borings, but the map sure shows they should have been. And in this case, we decided to go with shotcrete. We were going to do soil nails down here and rock bolts down here anyway. we decided to do it from the top so we wouldn't have this issue with the sand as we got down and started hoe ramming the rock. Now, the way that we dealt with utilities was to put micropiles in as reinforcement for the shotcrete. Not really reinforcement, but they helped with the cantilever moment before we could get the first rows of nails in. So we dealt with issues we had on the previous job and made things better on this one. You know, I got another story on that previous job. I can't see it. I went out there one day, I can't even remember why I was there, and I'm walking by, I probably parked on the job site to go to a doctor's appointment with somebody. But I'm walking around the job and I see these crane mats behind the micropiles. And I walk over to my contact at the GC and say, hey, what's up with those crane mats? We designed for 2 foot of traffic surcharge. There's roads all around here. We designed for 2 foot of traffic surcharge. But I didn't know you were putting a crane here. He said, hey, yeah, one of those big Manitowocks. It's, you know, it's like a tower crane, except it's on tracks. I said, whoa, whoa, whoa. We didn't design for that. And in the end, had them pick up the mats. We put in micropiles that then the mats sat on the micropiles. And nowadays, we'd have done CFA instead. Putting mats on micropiles is a little awkward. But so by walking on the site, I saved an unintentional surcharge that would have been really big. Okay, now we move to Morrow Park. So remember, this one's only 600 feet from the first one I showed you with the dry, lagging, and micropile shoring. But in this case, the sand, this is about 15 feet down to the water. So we were kind of lucky that we didn't have water on the other job because that was about the top of the cap rock. And then there was going to be another 5 foot of water before the bottom of excavation. And there was some more distance, I guess 7 feet left over till you get to the rock. So this maybe could have been dewatered. But the idea was, let's build a wall that becomes permanent and avoids this whole groundwater slurping, groundwater coming at you as you're putting in lagging issue. So this was done as a more contemporary secant pile wall. It's also a more contemporary job. That's where there's CAD files and images. So there it is. We use CFA primary piles, 900 millimeter and 80 millimeter secondary piles. Cross bracing, just because it could take one row of bracing and work. And we also didn't want to deal with anchors all around the utilities in the streets. Kind of an unusual choice for us. We sell a lot of anchors, but that's the way that one went. Another thing that happened on that job was we had a near miss with the work platforms. And there's going to be a work platform panel. I encourage you all to go to it. This is a modest size BG rig, BG22, 900 millimeter augers. The augers are clean, so there's no extra load from dirt on the augers. And they were tramming to a new drill hole location and ended up like this, and really it was the auger and the auger guide that stopped the rig from going over. And the guys got it righted. There's pictures of that, and they're scary looking, what it takes to strap onto the back of one of these and try to get it back. But the real interesting thing is the cause wasn't about, there was a clay subgrade where we're working at. There's clay above these terrace sands because of overbank deposits. So the clay subgrade wasn't that big of a problem. They put a foot of gravel over most of the site and things worked really well. But where he sunk in, they had gone in, the GC had gone in and dug a hole to remove an obstruction and then backfilled it poorly. And so we find those holes. So that's why you can't just say it's all the drilling contractor's responsibility to deal with these work platforms. The other lesson, that bullet point 4, I did not write. That's a quote, an exact quote from our project manager. I was using the Federation of Piling Specialist spreadsheet to calculate loads under these rigs, and learned in the process that this is not the best way. For the ground, this orientation is not the best way to drill. It's better for the ground if you drill at 90 degrees. And that, to most crane operators, that just seems completely ridiculous. But it's the truth, the way at least these European-style drills are built. So the Federation of Piling Specialists spreadsheet helped teach us a lesson that then we used on the rest of the project and didn't drive up the holes anymore, facing them. Okay, North Shore connectors, the last one, it's much more modern. This is the subway stuff that gets you over to the PNC Park and to the football stadium. If anybody got to go to the football game on Sunday, it was exciting. And on that project, at the station, we used a diaphragm wall with more modern technology. You'll see that in the pictures. And also cutter soil mixed walls for the rest of the walls. The project said that they should be soil mixed walls, and we chose cutter soil mix because we're owned by Solitunch. So in the midst of the project, we say, we're trying to figure out this ground for other issues, challenges with jet grouting. And the tunneling guy wanted to know more about it too. So we brought in a sonic rig, and the interesting, this is across the river now. This is on the city side, not on where the walls were. But the interesting thing with a sonic rig is you can get some pretty coarse samples out of the ground and have a much better feel for what the ground really looks like. And that box is either 6 or 8 inches wide, I can't remember. Should have had a ruler in the picture. But you know, those are 3 to 4 inch cobbles. Same in these boxes. So the cutter soil mixing uses a tool that looks like this. And you can imagine some 3 and 4 inch gravels are going to beat that tool up. And that we did find. We got the job done, another technical success, but it was a challenge. The other challenge, interesting challenge for a cutter soil mix, you know, the shales, this wasn't a clay shale at the bottom of the excavation. We did have to tow into rock. And the shales are generally fissile in a horizontal direction. So if you're coming down cutting like this onto a plateau, if you can't, you can dig the shales reasonably if you can get in there and peel them. But if you're hitting it like this, you can't get it peeled. So in the rock, we actually had to pre-bore to get so our teeth could get in there and peel it. But in the end, it was successful. It served the purpose. That's the launch pit. Kind of a skewed photograph. It didn't have a point. Well, maybe it was a fisheye lens. And the strengths were certainly well above what was required. But the drawback is boulders and rock are a big challenge for cutter soil mixing. And the grain sizes that came out of that Dick Gray report, we had Dick Gray come down, well, his guys, come down and take samples and of the alluvium in the launch pit area and take them back and run gradations. And you can see there was some amount of boulders and some big cobbles in there. And that was 40% of the samples, I think, were over 2 inches is what the outcome was. So sonic helps get you here, but it still might not find the really big ones, which you can find in a test pit. When it came to the diaphragm wall, I didn't include a whole lot of pictures of the details, but this used more modern technology with removable end stops that you leave in place until the next day, till you dig the secondary panel, and when you pull out those end stops, you can leave a PVC water stop in place. So when you go over and get off near the parking garage there in that station, that is permanently supported by a diaphragm wall with a very dense reinforcing cage. So our conclusions, it's good to have a lot of options for what you're choosing to do earth retention-wise around here. Sometimes we're driven by geology and certainly groundwater and alluvial deposits, especially fine to medium grain sands, is a big problem. And it's even worse when you have to slurp the water. And so, that led to a lot of decisions, but some decisions were made more driven by geometry or innovation. The PPG thing, soil nails were hot and sexy at the time, and I think that's part of what drove the desire to try them out. Okay, that's it. We got 9 minutes for questions. Oh, and if you're going to ask a question, please come up to the mic.
That's what I was going to say. I don't have any questions. I was just demonstrating how it's done, and now Sebastian will do the same thing.
I will demonstrate how the questions are done.
Most of the time when I give a talk around here, I tell Sebastian he's got to ask his questions last.
I know. And I mean, as always, great presentation by the two of you. I was just posted on LinkedIn. You guys are geotech icons in this region. You have done it. Oh, somebody didn't like that for me.
I liked it. I heard it. I'll repeat the question. Go ahead, ask a question.
No, I was going to say, I mean, as you show, you guys have done a lot of the work in this region. Very pioneer, very different methods. As you were saying, soil nails were hot and sexy at some point, right? And different evolutions. I mean, I think Pittsburgh in general, we are a town of solid panel lagging, driven pile, drill shafts, micropiles, things like that. But there is one of your presentation that caught my eye, which is the slurping. Because we haven't really have, I mean, you saw some projects, but if you go on transportation, it's very limited what we have done with the slaughter walls and things like that. In your opinion, and why is that? I mean, what exactly is the conditions here that are not very favorable, that we tend to go into all these other technologies rather than doing
I think it's project geometry. So, where you need a diaphragm wall, it's when you're going below the groundwater table in granular material or permeable material. And you can't, and you don't want to dewater, or slurping makes it a challenge to dewater. So the transportation projects don't really need that, right? They're not the deep excavations. I'm sure that if a PPG was going to be done again now, we'd be selling them permanent D-walls as a permanent basement wall. And why that doesn't get done on more is you have to incorporate the diaphragm wall into the permanent structure for it to be cost effective. And even then, it's still, you almost have to choose it as a risk mitigation strategy. There are successful beam and lagging jobs done around here. That PPG was beam and lagging, and I don't know how they deal with the water at the bottom, because given our experience dealing with water on other places, it's just really tough. I don't know how they deal with installing the lagging.
Yeah. All right. Well, thank you. Congratulations again.
Hey, Tom. Thanks. It was really, really fun to listen. And, you taught me some things that I didn't remember. But I wanted to help you out at least on two things. One was my recollection has to do with again, on the diaphragm wall question, at the soldiers and sailors. Slurry wall, diaphragm wall. The client wanted zero lot line construction. To build a temporary shoring and then permanent walls inside the garage was more costly. And it's possible that, yes, it was driven by this dewatering thing, but frankly, I don't recall the dewatering thing and never even heard of the slurping thing. So you might have got a different version of the story when you spoke to others. Maybe a Dan.
I always thought that holiday and experience was what led University of Pittsburgh to want that.
We proposed the diaphragm wall to them, from what I recall. Yeah. So, but it definitely had the sand profile in it. But the architect loved it. He said, I love the organic nature of it because it's picking up an imprint of the soil layers. And it really does if you look down there carefully.
Yeah, you can say the same about the tangent wall. You gotta love geology to love the look of a diaphragm wall or a secant pile wall.
But I wanted to clarify something else on the monstrosity. I don't know, I don't know if you know, I think we built that like right before you got hired, like 88, something like that. And it might have even been 87. But that wall was cut in like sandstone. And we told the client we're either going to bolt it or anchor it on the way down, but the specification said an anchored soldier pile wall, okay? And we went to the client and said, well, you don't need soldier piles here. We can anchor this on the way down, or even in some, even use just bonded rock bolts and build you a concrete wall. We could give you an architectural finish. We can make it look pretty nice. The client said, no, my spec says soldier piles, and you're going to give me soldier piles. So we cut the rock, drilled the anchors on the way down, stood up the soldier piles on some rock bolts and a base plate after some argument that counted as a socket, stood up the piles, threaded the anchors through the wall, slid in all the panels, threw some gravel in the back, and tightened it all up. It didn't really need a wall there. The loads were calculated using some imagined friction angle on the valley stress relief joints in the rock. It was like hardly any load on the thing. So there's more to that story than what the newspaper said, but we, of course, couldn't say.
But you will admit that more precast joints would make it look better.
Well, sure, probably. Yeah. But at that
I thought
point,
that's why they called it
but
monstrosity.
the client had put a financial pressure on us at that point because we had assumed we could build the job
Yeah.
and make it look nice, and the beams were expensive. Yeah. Okay. Thanks.
It's good to see you guys playing together nice this morning, right? Great presentation. Question for you. I think it was on the UPMC job where you had the micro piles used as, I guess, in lieu of soldier piles, right?
Yeah.
So the picture was facing on, but when you get below the soldier piles, how close or what was your offset so you don't have any issues with exposing the sockets below grade?
Well,
How much of the rock were you chopping?
It didn't matter much.
Okay.
I had trouble. Okay. So the only
10
thing,
slides back.
it couldn't fall away vertically. The toe in the rock was only so that we could get down and put in toe ties. So
Okay, so you did have toe ties.
structurally, we didn't have a lateral load applied to that cap rock in the end. So here, there's toe ties. That's a little whale and a bar into the rock. So we still had to support the rock, but it's not like we had a unreinforced rock shelf. There were rock bolts put into that rock to keep it back. So it's got handled by the rock bolt work and the toe ties.
Got it. Thank you so much.
Is that it?